Since we're talking about force, even though it's an electrical force, that brings us right back to Sir Isaac Newton. Newton's first law, the law of inertia, states that objects at rest tend to stay at rest unless an external net force acts on the object. This, of course, is just a more specific statement of objects in motion tend to stay in motion. In this case, the velocity is zero, so it has a velocity of zero in the beginning, it has a velocity of zero at the end. In this case, the free rod accelerated towards the stationary rod. It had an initial velocity of zero, and then it had a velocity, so change in velocity over time, you have an acceleration. If you have an acceleration, you must have a force. We call this the electrical force, and as with all forces, it is measured in newtons. So whether it's a mechanical force, electrical force, it's still newtons. First, a little historical background. In the late 18th century, several physicists, Joseph Priestley and John Robison, for example, reasoned, and Robison measured. So reasoning is always good, but in physics, until you measure something, you really don't understand what you have. But they basically reasoned, and then Robison proved that the force between two objects followed the same principles as gravitational force, and that the force between two charged objects depended on the inverse square of the distance between them. You can see right here, force, and this little squiggly sign here, that means proportional to 1 over r squared. That means the further you get away, the smaller the force is. Charles Coulomb then came along, and in 1785 he published a paper that he based on very detailed experiments that definitively proved the above, that it was an inverse square relationship. He used a torsion balance, which is the same type of apparatus that Henry Cavendish used to measure the gravitational constant. So you can start seeing a thread here, some relationships between the electrical force and the gravitational force. Okay, this is quite a busy slide, but let's take it piece by piece and see if we can make it a little less intimidating. Right here in the box, that's Coulomb's law. The force, the electrical force, and you can see how it's F sub E, F means force, E is electrical, is equal to K, which is the Coulomb constant, obviously named after Charles Coulomb, and that's just a number. That number stays the same anywhere in the universe. Q1 and Q2, those are two charges that we want to measure the force between, and we use an absolute value sign. We just want the positive force here, and we'll get to that later. And R12, all that means is it's the distance between charges 1 and 2. And then the squared part is right up above that. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. And you can see, if you do some unit cancellation, that when you multiply two charges and divide by distance squared, you multiply it by K, you're going to wind up with the unit of newtons. Newtons is the only guy that survives, right? You have meters squared in K, that'll cancel out with the meters squared here. And the other part of K is divide by Coulomb squared, and that will cancel out with the Coulomb times Coulomb, or Coulomb squared, so you're left with newtons. Note the striking mathematical similarity to Newton's law of gravitation, right? If we were to write Newton's law of gravitation, that would be Fg equals G, which is the universal gravitational constant, m1, that's one mass, m2 the other, and then the distance between them we write as r12 quantity squared. Coulomb's law is used to calculate the magnitude of the force. Each charged object exerts the same force on the other one, except in opposite directions. Once again, Newton comes into play. Newton's third law applies to all forces, not just mechanical ones. Since electrical force, like all forces, is a vector, you need to specify the direction of the force magnitude determined by Coulomb's law. And what you have to do there is look at the signs of both charges. So if I have a positive charge here, and I have a negative charge over here, we know opposites attract, so let's call this charge 1, this charge 2. So charge 2 is going to attract charge 1 like that. Charge 1 will attract charge 2. And I just use a little notation here where this force here is the force that charge 2 exerts on charge 1, and right here, this would be the force that charge 1 exerts on charge 2. Some textbooks use the exact opposite convention. It's frankly whatever makes you and your teacher, your students most comfortable, but this is the one I use. Now, F21 exactly equals F12 in terms of magnitude, but if we want to talk about them as vectors, we would have F21 as a vector equals the negative of F12. All that states is that they're equal and opposite in accordance with Newton's third law. This is one of the more amazing things of living in our universe. You have two, on the surface, very different forces. You've got electrical force and you've got gravitational force. However, both of them have very similar mathematical equations. The magnitudes of both forces decrease as 1 over r squared. And for example, instead of the charges or Q's in the electrical force, you have masses or M's in the gravitational force. And instead of the Coulomb constant K for the electrical force, you have big G, the universal gravitational constant for gravity. A big difference, however, gravitational force is always attractive. There is no anti-gravity. However, electrical force can be attractive. The two charges can attract each other if they're different, or repulsive, like charges repel. And one further difference is, look at this number right here. The electrical force is on the order of 10 to the 36 times as strong as the gravitational force. The reason we notice gravity all the time, we are stuck to the Earth, is because of the tremendous mass of the Earth. But if you just compare the forces similarly, the electrical force is far stronger.